Good morning, my dear students. Uh, in this session, we will see one more example on three-hinged parabolic arch. Proceeding to the solution, the question is, a three-hinged parabolic arch is loaded as shown in the figure. That is what you are looking at it in this diagram. It has a span of 40 meters and rise 8 meters. And you have a portion BC loaded with UDL of 10 kilonewton per meter uh, on the right half of the arch, if you observe clearly, which means for a span of 20 meters. And you have a point load 40 kilonewton on left half of the portion AC. It is at a distance of 10 meters from support A. So a three-hinged parabolic arch is given. It is a parabolic arch, and you see to calculate the location and magnitude of maximum bending moment in the arch. So this is what we need. So to calculate the location and magnitude of maximum bending moment in the arch. So you need to draw BMD. That can be done by writing MX equation as you have done in case of your beams. Okay, right. Let us proceed to the solution. And you know that this solution starts from the free body diagram of full arch. So taking the arch ACB, then writing three equilibrium equations. Okay, so that part we need to complete first. So coming to that, so how do you find the vertical reactions? So to start with, we will solve for RAY value. Okay, so this is what is right. This is what is solved for RAY value. Right, how do you get this value? It is by taking moment of all the forces about B. Okay, so when you take free body diagram of full arch ACB, so this is where you are taking moment center, the point B, and you are applying equilibrium equation sigma MB0. So if you do that, we start with say RAY into distance is 40 meters. Okay, so RAY into 40, which is clockwise, and then HA pass through point B, so moment is 0 from HA, and then 40 into the distance is now 20 plus 10, it will be 30, or otherwise 40 minus 10, anything is okay. Okay, so what you write here is the equation RAY into 40. So if you say clockwise positive, it is positive. Okay, so otherwise if you say clockwise negative, you can take it as negative. So that depends on the individual who is solving the problem. Okay, so this is moment from RA is RA into 40, and moment from 40 kilonewton, that is point load, is 40 into the distance is 30, Then moment from UDL is 10 into 20, the total load which will act at the center of 20 meters, which means it is 10 from B. Okay, so moment from 10 kilonewton per meter is 10 into 20 total load into the distance 10. So this is how we write the moment value, right? So that is what is seen here. So 40 into 30 is moment from point load, and 10 into 20 total load into distance 20 by 2, that means 10. So this is RAY into 40. The 40 has come to denominator. So it is straight away, instead of writing the equation like RAY into 40 minus 40 into 30 minus 10 into 20 into 10, it is given directly in this formula, right? So first you need to write the equation, then you will lead to this step, okay, and that will give you Ra value as 80 kilonewtons, right? If you apply sigma Fy0, the another equilibrium equation will give you Rb value, okay. So how do you get that value? What is the total load? It is 40 point load and plus right, let me clear that extra line that appeared. Right, 40 plus, and the other load is wait, I'll write it. Okay, so UDL, that 10 into 20. So total load is 40 plus 30, total 70. So total load minus RA, okay, right? So RB value, this is 40 here plus 10 into 20, 200 plus 40 will become 240 is the total load value, right? So 240 minus RA, that means 240 minus 80 will become RB as 160. So total 240. So this is from one more equilibrium equation. Then to find H value, what we will be doing? We will be considering one half of the arch, either AC or BC, and you are going to write moment at C is equal to 0. That is the third equation that you need to write. So MC is equal to 0 will be giving you, by considering only half of the arch, maybe AC portion or BC portion, whichever you take, you will get the same value of H. So let us see what is being considered here. So making use of the condition that moment at hinge C, left of hinge C is 0 taken. So which means it is written for portion AC, left of hinge is taken. So what are all forces you have to the left of hinge? You have three forces to the left of C. What you have is RA and HA and 40. So you need to write moment about C for all these three forces. So RA into this distance is 20, and then h into the height is 8, and then 40 into this distance is 10. So that is written here. So ray into 20, moment from ra, ha into 8, moment from h, and moment from 40. Okay, so that is mc value, moment at c, total value. And you know ra value, that is 80, substitute it here, and you want ha value, that is 150, same as hb, 150, but the direction is opposite, right? So this is how we solve for four unknowns present in the arch, which are external reactions. So ha ra, two reactions at a, and rb hb, two reactions at b. So total four reactions you are able to find. So ra value, what you got is 80, rb is 160, and h is 150. Okay, so hope you got this procedure uh, very well, to remember always that if you want to solve an arch problem, a three hinged arch problem, first you shall be able to solve for external support reactions. Otherwise, you cannot proceed for any of the questions asked to find maybe bending moment or normal thrust or radial shear anywhere in the arch. So any question on internal forces, that means bending moment, normal thrust, radial shear, you will be able to solve these three only when you are able to solve for support reactions first. That means there will be four unknowns because you have two hinges at two ends. Each hinge will have two reactions. So total four reactions, but you are able to apply three equilibrium equations, and the other equation what we use is the hinge, internal hinge condition. That means moment at c is equal to 0. So this is how you are able to solve the external support reaction. Then let us see what next we will be doing. So to find maximum bending moment, so you can see that consider a section x from end B. Moment at section x in portion CB of the arch is given by, so you have some mx equation. Okay, right. Why portion CB is selected? That is a question. First, you need to understand. Now you come back to the diagram and the values. Let us see. Okay, so you can see the reaction at B is almost double to support A, and the load is on the right half of the arch. The load is 200 kilonewtons. That means 20 into 10, 200 kilonewtons is the total load. So there is a heavy load on portion BC and less load on portion AC. It is only 40, whereas 5 times load is acting on portion BC. Hence, we expect maximum bending moment in portion BC, not in portion AC, right? That is the reason why it is selected portion BC is selected for searching maximum bending moment location. Okay, right. What we do now, we take some section X in portion BC and we write MX equation. So let us see how do you write MX equation. Okay, so this is let me clear all that what is written. Okay, so that we get some space, clear space to write. Right, I think you understood why we have selected the portion BC for maximum bending moment location. Searching for maximum bending moment location. Okay, right, let me uh, take a section, X at a distance of X from B. So now you need to write moment at this section MX. So how do you write MX? That is the next question. So MX, sum of all moments to the right. So what you have here, it is 160. And what you have the force here, it is 150. And you have load UDL only to this part, which is X. Okay, I think you got it. So to write MX now, sum of all moments to the right. So what we will do, I told you that whenever you write moment at a section, you should follow the notations. Okay, right. So sign convention, I mean to say. So 160 into X is going to be anti-clockwise. Okay, so write anti-clockwise positive. Next, it will be minus 150. So this is the force acting, and this is the distance 150. So that we will write as Y. So 150 into Y. Force is horizontal. So what we want is vertical distance Y. Right, what next you have? UDL. So that is going to be again clockwise. So moment from 150 is also clockwise, hence we take minus. So right clockwise negative. Okay, got it. Right anti-clockwise positive. So minus 10 into distance, I mean to say span is X. So 10 into X is total load, where that will act center of X. So distance between section and the load is X by 2. Right, this is MX. So what you will do now, replace for Y. What is Y? Okay, so that is what you observe even in the equation here. Now you see 160 into X minus 150 into what is this? Is Y minus 10 into X by 2, 10 into X square by 2. Then what is Y? In the initial step itself in this slide, you will find what is Y. It is by the formula that we already used, that, okay, 4hx into L minus X by L square. Okay, that is always there. Okay, so this is what you need to use for y, 4hx into L minus x by L square, right? So that will give you y value. Substitute into this equation in place of y, and you will have mx equation ready for differentiation to search for maximum or minimum. So what you need to do now, differentiate the mx equation with respect to x, equate it to 0, you will get x value, right? So this is dou mx by dou x. So 160 into x, so dou by dou x of x is 1, it is 160, and 150 is a multiplier and it is a constant. 8 by 10 into dou by dou x of x is 1, and 8 by 400 x square differentiation 2x, and 10 by 2 x square differentiation 2x, so 2 gets cancelled, it will be 10x. So simplifying this, you get 40 minus 4x is 0, and x is equal to 10 meters. So this is where we expect maximum bending moment to occur. What is that location? X is 10 from B. This is total 20. Okay. 10 means it is exactly midpoint of BC. Midpoint of BC. Right. That is where you need to get a value of maximum bending moment. How do you get it? It is by substituting x value into this equation. So substitute x value into that equation. At 160 into x 10, 8 by 10 into x, 8 by 400 into x square, so 10 by 2 x square. So maximum bending moment in the arch is 200 kilonewton meter. Okay, right? So what next you need to proceed for? So location and magnitude of maximum bending moment in the arch is found. So what you need to do now, draw bending moment diagram. Okay, so you know that the bending moment is 0 at A, bending moment is 0 at C, 0, 0, and you have bending moment 0 at B also, and you have maximum bending moment of 200 kilonewton meter at midpoint of BC. Okay, this is midpoint of BC, right? So now what you need, the other value to complete BMD, only the value of bending moment at the point load. Okay, if you are able to solve this one, and you can complete the bending moment diagram. Okay, it's very simple to calculate bending moment under point load 40 kilonewtons. How do you get it? Sum of all moments to the left, if you take, you will get bending moment. I'll just write the value, you check with the values. It is 80 RA into distance 10. Okay, then right, this is y value. So HA is say this is left clockwise positive, so I should write minus 150 is H value into y. So this is bending moment under 40 kilonewton load. Okay, so once you substitute for y value, then you are going to get this value. So how do you complete the bending moment diagram? It is as good as your beam now. So, if you can take a reference line like this, so maximum bending moment in AC portion, definitely we will expect under point load. It is a well known fact. So it is like linear. So 0 at C, 0 at A, we write a triangle, and then parabolic in this portion BC. Okay, so that we will draw this bending moment. I think it is better to draw it in a separate sheet. Okay, so this is right. Let me clear all these things. So how do you draw BMD for this case? So the calculation part, you just proceed with your calculator, then get a value. I'll just do it for a rough value, because you need to estimate y value, then you need to draw it. Okay, right. If you observe that the nature of bending moment diagram in the arches, then only you are able to draw them. Okay, so how do you proceed for drawing BMD is again a different task, because MX equation, if you see that the MX value is proportional to X in first term. Okay, and MX equation is proportional to Y in second term. So how you see it here itself? So can see, so if you take mx equation that we already wrote somewhere here, yes, okay, so this mx equation, whatever is given here, is proportional to x in first term. You see this one, so mx is proportional to x, so it is no, and mx is proportional to x square here, and the third term is also x square. So mx is finally, that means bending moment is finally proportional to x square, irrespective of the load, whether it is point load or UDL, whatever it is. Even you see this portion BC, you are having UDL. So whatever may be, whether it is a point load or UDL, why you are getting this behavior of bending moment as parabola? Because you have a term y in bending moment always. So y is always proportional to x square. So with that conclusion, the bending moment is always proportional to x square. So parabolic in nature. So that's why you should be drawing the two parabolic portions in AC and BC. So this is zero bending moment, and you estimate some value at this. So we will draw that, and you have 200 kilonewtons, which is kilonewton meter maximum value. So we'll go for like this. So mention whether it is sagging or positive or hogging according to that nature. Okay, according to the nature of the values. Okay, so that's how it is to draw BMD for this case. Okay, so this is how you solve for a three hinged parabolic arch with point load and UDL to practice one more example to practice. Okay, right. Thank you so much.